This lesson is a wrap-up of what we've seen so far. The working file is called wrapup1.txt. So let's go back to where we began. The general topic is concurrency, parallelism, and non-blocking I/O. To begin, concurrency and parallelism are closely related but distinct. So for example, on a single processor machine, you can have concurrent applications, but you can't have parallel applications. True parallelism requires multiple processors, so you have to be able to be doing literally multiple things at the same time. Concurrency is slightly different. Concurrency means doing many things within the same time span. That would cover, of course, parallelism, but you may do one thing, switch quickly to another, switch back to the first, and so forth. So concurrency is absolutely possible on a single processor machine. The great appeal of parallelism is this: it's a natural way to do concurrency. It also is an efficient way to do concurrency, because when you go parallel, what you're doing in effect is boosting performance. Since you're doing more than one thing at the same time, your throughput increases. In other words, the amount of work you get done in a given time period is going to increase, and that means, in everyday terms, higher performance. So it's a great thing. And parallelism, as we'll get back to a bit later, has become the chief approach to boosting performance nowadays. Now, there are two classic approaches to concurrency, and that is multiprocessing and multithreading. I still owe you technical definitions for both processes and threads, and I'll provide those, but right now I'm going to rely on your intuitions and your experience as programmers. So multiprocessing and multithreading are related, but they are distinct approaches. Sometimes they're used together. We'll see examples of that fairly quickly, but they are distinct. So for example, some web servers, Nginx is an example, favors multiprocessing. Other web servers, the Java-based Tomcat web server, favors multithreading. Non-blocking I/O as a concurrency mechanism is not quite on the same level. In theory, it might be a third option, but in practice, it's really emerged as an attendant to one of the other approaches. In other words, what you tend to see is multiprocessing plus non-blocking I/O. Nginx, by the way, uses that. Or, as in the case of the Node.js framework, non-blocking I/O combined with multithreading. So we'll have plenty of time to look at hybrid approaches that combine multiprocessing, multithreading, and non-blocking I/O in different ways. Now, let me get back to the summary of the languages we're going to look at, beginning with C. C is very close to the metal. The standard operating system libraries are written in C. The kernel code is written in C, perhaps with a bit of assembly. So C is as close to the metal as we'd like to get. The code is fairly reasonable. Most modern languages have copied a lot of C syntax, so even if you've not seen C before, I think you're going to find it fairly easy to read and to understand. Whatever the application language, and this is the second bullet point at the end, it's important to keep in mind that everything is going ultimately through the standard libraries, again, through C code, and from the standard libraries for the stuff we're going to be doing, into kernel code. So even if we're not writing in C, you might say we're using, in effect, C code. Now, higher level languages, Java and C#, Go, Node.js, Ruby, Python, and so forth, these languages have different styles and different strengths for managing concurrency. Java and C#, for example, favor multithreading. Perl and, for example, Ruby favor multiprocessing. We'll have time to look at examples of how languages favor a particular approach. The only thing we'd like to keep in mind right now is that different languages have different strengths when it comes to concurrency management.